Okay, we'll get started with the next talk. So I'm very happy to introduce Matthew Meglio, who will be talking to us about recognizing retromorphisms retrospectively. Take it away, Matt. And you're still on mute.
How's that?
That's great. Thank you.
Better. Cool. Awesome. Well, thank you, Bryce. And yeah, thanks to both Bryce and Tim for giving me the invitation to talk to you all today. So this talk is going to be a gentle introduction to this notion that Bryce and I are calling retromorphisms. So we're going to start with a bunch of examples of morphisms across different branches of mathematics, which have a similar kind of flavor. And then we're going to see a double categorical construction, which sort of unifies all of these notions together. And this work is a natural continuation of the work that Bryce and I have done on cofunctors and lenses into other more general settings. But let's start. So cool. So we're interested today in looking at mathematical structures with two components. So we'll see a bunch of examples of these in a minute. And we're going to use these two terms, morphisms and retromorphisms. So we're going to use the term morphism for the morphisms that act on both of the components of the structures in the same direction. And we're going to use the term retromorphism for morphisms that act on them in opposite directions. And usually the action in the backwards direction has like a kind of lifting flavor. So again, we'll see this in the examples in a moment. But before we get there, I should point out that this retro prefix that we've adopted comes from Perret's retro cells that were introduced in one of his talks a few years ago, and we will see later in the talk what these retro cells are. So the first example that we're going to consider is that of categories. So the two components of a category that we're interested in are the objects and the families of morphisms between the objects. Now, functors are the morphisms between categories. So a functor acts on both the objects and the morphisms of a category in the same direction. So it has an object map and a morphism map. And obviously the morphism map is compatible with the object map, and we have compatibility with identities and composites. But so yeah, the functors are the morphisms of categories. What are less commonly considered, but certainly more recent interest, is this notion of cofunctor. So a cofunctor between categories, phi from C to D, consists of a function between their object sets. So every object in C gets mapped to an object in D, but the action on morphisms is in the other direction. So for every object A in C and every morphism G out of phi of A, there's a lift of G to A, which I'm denoting phi superscript A of G. And these lifts should also be compatible with identities and composites. So cofunctors, I think, have become quite popular in recent years in the applied category theory community because they're useful for modeling things to do with synchronization of systems. Now, you're probably wondering why I've crossed out the co and replaced it with the word retro. And that's because in this talk, I'm trying out a slightly different name for cofunctors. So I think it's generally accepted that the name cofunctor isn't the best name because it isn't a functor between opposite categories, nor is it a contravariant functor. And since we're sort of using this retro prefix more generally for this flavor of lifting morphism, I'm trying out the name retrofunctor, and I'm interested to hear people's thoughts on whether this is a good name or not for or whether it's a better name than cofunctor for this particular concept. But anyway, in this talk, I'm going to refer to these things as retrofunctors. Now, thanks to, I believe, Arman and Ustalu, we know that when you have a functor and a retrofunctor that are compatible in an appropriate in the appropriate sense, what we have is the same thing as a delta lens. So a delta lens is a construct that was introduced by Zinovi-Diskin to model synchronization of systems. And so it's quite nice that these morphisms and retromorphisms come together in a way to give a structure that's already known elsewhere in mathematics. So this is my first main example that we're going to have in the back of our mind as we go through the talk. So for the next example, we're going to think about metric spaces, or should I say Levier metric spaces. So these are actually examples of enriched categories, but for now, we're just going to consider the specific case of Levier metric spaces. So the morphisms of metric spaces are the non-expansive maps. So the non-expansive maps are, so a metric space, I should probably start off with, a metric space again has two components, the points of the space and the distances between them. And so a non-expansive map is a function between the points, but it also acts on the distances in the same direction. So the distance between a point X and a point A in the codomain should be greater than or equal to the distance between f of X and f of A in the, I must have said codomain before, in the codomain. So domain to codomain. Anyway, I'm mixing up my words. Another way of thinking about it is this picture here. So if I have a point X in the domain and I look at the open ball of radius r around X, then F should map this open ball into the open ball of radius r around f of X. So these two characterizations are equivalent. And again, for metric spaces, there is also a notion of retromorphism, but these, I believe, I haven't seen anywhere, although it wouldn't surprise me if they've appeared in the literature somewhere. They're very closely related to something called a submetry, as we'll see in a moment. But I'm going to call these things retro non-expansive maps because they're non-expansive in the reverse direction in some sense. So one sort of characterization of retro non-expansive maps is for every point X in the domain and every point Y in the codomain, the distance from phi of X to Y should be greater than or equal to the infimum over all points in the fiber over Y of the distance between X and A. So that's one way of characterizing the retro non-expansive maps. Equivalently, we could say that for each point X in X, the open ball of radius r around X is mapped to some set in Y that contains the open ball of radius r around phi of X. So these two characterizations are equivalent. So these retro non-expansive maps are non-expansive in the reverse direction in some sense. Now, when we have a non-expansive map and a retro non-expansive map, what we get is actually a known kind of morphism in the literature on metric spaces. It's called the weak submetry. And I should thank Callum Reeder and Paolo Perrone for pointing us to the notions of submetry and weak submetry. I think it's quite interesting that it comes up in this way. So this is our second example, and I guess what this has in common with the first example is both of these are examples of enriched categories. So categories are categories enriched in set. Metric spaces are categories enriched in the positive reals, so the interval 0 to infinity. And so in the remainder of the talk, when I do the double categorical construction that gives these examples, I'm going to do it in the more general case of enriched categories, as we'll see in a moment. Now, for the third example, I'm going to talk about topological spaces. So here, the two components. So the first component is the points of the topological space. And the second component Well, it depends on your definition of topological space, because there's a few equivalent definitions, but the usual one, it would be the open sets of the topological space. But equivalently, the second component could be the neighborhoods of the topological space, the neighborhood filters. In any case, again, there's two natural kinds of morphisms between topological spaces that we're interested in. So the continuous maps are the morphisms of topological spaces. Now, the definition of continuous map that I expect most of you are familiar with is the one that says that the preimage of every open set is open. But there is another equivalent definition that more closely mirrors the examples that we've seen on the previous slides. And that's in terms of this notion called a filter, and in terms of filter convergence. So if you don't know what a filter is, then I'll just give you the intuition that you should think of filters as like generalized sequences. So filters, I mean, they play a similar role to nets, perhaps, if you've heard of nets before. But the idea is many of the nice properties about sequences that hold in metric spaces hold about filters or nets for topological spaces. So in particular, there's a notion of convergence of filters to points. And so a continuous map can be equivalently characterized as one for which whenever you have a filter on X that converges to a point little x, then the direct image of that filter converges to the image of that point. So, and this should look similar to, for instance, the, a functor between categories. It has that kind of flavor. So the other kind of morphism between topological spaces, so the retromorphisms of topological spaces, are the open maps. And again, the characterization of open maps that I expect most of you would be familiar with is the one that says, well, it preserves, so the direct image of every open set is open. But there is another characterization of open maps that more closely mirrors the other examples of retromorphisms that we're seeing in terms of some kind of lifting property. So what this lifting property says is that if I have a point little x in X, and I have a filter big Y on Y that converges to 5x, then there's a lift of that filter to X. So there's a filter big X on X whose image is Y and which converges to X. So this is an equivalent characterization of what it means to be an open map. And I guess the point of giving this characterization is to show how open maps have this kind of lifting property. This explains why we might expect to think of them as retromorphisms. And I mean, I haven't written it up here, but it's quite common to consider maps that are both open and continuous. But there's, as far as I'm aware, there's no special name for this, usually just open continuous maps. So just to summarize the examples that I've given so far. So we've seen categories, metric spaces, and topological spaces. And the morphisms in each case are the functors, the non-expanding maps, and the continuous maps. The retromorphisms are the retrofunctors, the retro non-expanding maps, and the open maps. And the sort of compatible pairs of morphisms and retromorphisms are called delta lenses, weak submetries, and open continuous maps. And I've included this little note here enriched to just remind us that these first two examples are both examples of categories enriched in a monoidal category. And from this point onwards, when I go through the double categorical theory from which these ideas arise, I'm going to deal with the more general enriched category setting for which these two are particular examples. Okay, so I've given a bunch of examples of things that seem to have a similar flavor. And now it's time to back that up with the double categorical machinery that from which these concepts arise. So I should start first by introducing the double categories of interest. And I guess I should thank Bob Perret for the talk before me for introducing a lot of the basic double categorical notions that I'm going to need, but I will remind you of them anyway. So, so a double category, as Bob said, is a category where you have two kinds of morphisms and a way of talking about compatibility between them. So in my notation, I'm going, rather than talking about horizontal and vertical arrows, because often there's different conventions as to which direction is the direction which is sort of only unital and associative up to isomorphism. I'm going to talk about arrows and pro-arrows. So the arrows, that's going to be the direction that's strictly unital and associative. The pro-arrows is going to be the direction that's associative and unital up to isomorphism. So we have two kinds of morphisms, so they can be composed together. And then we have these cells, which again compose in both directions. And so yeah, so that's all I'm going to say about recapping concepts from double categories. But we're going to talk about some examples. So the first example is the one from which we're going to get the theory of enriched categories. So V here is going to be a distributive monoidal category, and I'll explain why we need the distributivity in a moment. But we're going to define this double category VMAT of matrices in V. So the objects of this double category are just sets, and the arrows, so this is the strictly unital and associative direction, are just the functions. So it's the pro-arrow direction that's interesting. So a pro-arrow M from A to B is going to be a matrix. So we think of the columns as indexed by the set A and the rows as indexed by the set B. And it's a matrix of objects of V. Now, in order to talk about composition of these matrices, this is where the coproduct of our monoidal category comes in. So coproduct is a part of the distributivity assumption. So it's the usual matrix product formed. So the sum is given by the coproduct and the multiplication is given by the tensor product. And the distributivity is needed, I'm pretty sure, in order to guarantee that we have the associativity up to isomorphism. So these are the pro arrows, and then the cells are these matrices of morphisms, these sort of equivariant morphisms. So if I have a matrix M from A to B and a matrix N from C to D, and then I have functions from A to C and B to D, then this cell alpha has components. So an AB component is a morphism from the AB entry of M to the F of A, G of B entry of N. So this gives us a double category. And as I said, this double category is the one from which we're going to derive various enriched category notions. So the second double category that I want to introduce is the one from which we're going to get the topological notions. So first, I should say that this curly F is the filter monad on set. So it sends a set to the set of filters on that set. And again, I'm not really going to say much about what a filter is. Well, I guess I can say that it is a set of subsets of a set. And so it's a bit similar to the power set monad. So in particular, you have an ordering between filters, and that's going to be important for defining the cells here. So I've written KL lax of F, and this is, I guess, a bit of informal notation because it's like the Kleisli double category of the monad F that Bob defined in his talk, the previous talk, except that for the cells, we're allowing more than just equality of around the boundary, but we're using this ability to order the filters on a set to allow for inequality here. So this is where the laxness comes in. So what is this double category? Well, again, it's objects and its arrows are just sets and functions. But the pro-arrows now are Kleisli morphisms of the filter monad, and they compose using Kleisli composition. And as I said, so it's a flat double category. So a cell, either a cell exists or it doesn't. And in this case, it exists if when I take the Kleisli morphism M from A to B and compose it with the image of G in the filter monad. So that gives us a morphism from A to F of D. So that's one morphism. Going around the other way, I get another morphism from A to F of D, and I can sort of look at them pointwise. And so for each point in A, I get two filters on D, and the cell exists if one of those filters contains the other. So if this G of MA contains N of FA. So this is incorporating this order structure on the set of filters on a set. So this is the second double category of interest to us today. And as I said, from this double category, we're going to get various topological notions. Cool. So they're the two double categories that we're going to talk about. So the next thing that I need to introduce is the notion of monad in a double category. Now, I should say that this is not the same as the monads that Perret was talking about in the previous talk, because Perret was talking about monads on a category and then talking about how they form a double category in some sense. But here we're talking about monads in a double category. So I just wanted to make sure that it was clear that we're not quite talking, I mean, they're obviously related, but then it's not exactly the same thing. So a monad in a double category is an endo-pro-arrow. So it consists of an object of the double category and a pro-arrow T from A to A, equipped with cells, so the unit cell and the multiplication cell. So these are in the, I guess, it doesn't matter. Anyway, so it has a unit cell and a multiplication cell, and these should satisfy the usual unitality and associativity axioms. So, I mean, if you've seen monads in other contexts, then you should be able to guess what these axioms are, but I'm going to show you briefly anyway. So here's the unitality axiom, and here's the associativity axiom. And I guess I've included these so that if you want to look at the slides later, you can go back and have a think about them. But I think more important for the talk is what are some examples of monads in double categories. And so the first double category that we're going to consider is that double category of matrices in V that I introduced before. And so monads in VMAT turn out to be V-enriched categories. So how does this work? Well, remember, a monad is an endo-pro-arrow. So it consists of an object of the double category. So an object of VMAT is a set. So this is going to be the set of objects, and an endo pro-arrow on that object. So a pro-arrow in VMAT is a matrix of objects of V. So for every pair of elements of the set C-ob, so for each A and B that are objects, there's a lot of objects, but anyway, for every A and B that are objects of this V category that I'm defining, I have this Hom object, CAB, which is an object of the monoidal category V. And then, so we have this unit cell here is a matrix of morphisms from the identity matrix on C-ob to the matrix of Hom objects. And if you think about what a matrix of morphisms out of the identity matrix looks like, well, for all the entries that are 0, there's only a unique such morphism. So they don't give you any information. So the ones that are interesting are the morphisms out of the monoidal units, which are on the diagonal. And so these give us the identity elements of our V-enriched category. So I'm denoting these by JA, goes from the monoidal unit I to the diagonal of C. Similarly, so this multiplication cell for the monad gives us the composition maps. So if you think about what we have on the left here, we have the product of the matrix C with itself, And that matrix product is really some sum over all of the objects in the middle of the tensor product of, CA with that object, with C of that object with this little c. And so if you use the universal property of the coproduct, then you can sort of split that out into a family of morphisms, and you get these morphisms here. So M, little a, little b, little c is a morphism these are the composition maps of your V-enriched category. And the unitality and associativity axioms of the monad tell you that the identity elements are identities with respect to composition, and that the composition maps are associative. So this is exactly what it means to be a V-enriched category. So moving on, we're going to look at monads in this Lax-Kleisley double category of the filter monad, and these turn out to be topological spaces. So how does that come about? Well, so recall that a monad in this double category should be an endo-pro arrow. So the object, which is the set, is going to be the set of points of the topological space. And the endo-pro arrow itself, so it's a Kleisley morphism for the filter monad. So it's a function from X into the set of filters on X. So in other words, for every element of X, we have a filter, and this is going to be the neighborhood filter of X. And so the existence of the unit cell, when you unpack what it means, amounts to asking that every neighborhood of X contains the point X, and the existence of the multiplication map, when you unpack what it means, amounts to asking that every subset of X has open interior. And I guess for that to make sense, you need to have an appropriate definition of what it means for a set to be open and what it means for the interior of a set. And this is all in terms of neighborhoods, because but once you have all of these axioms, you get a structure that is equivalent to what most people usually think of as a topological space, which is a set X equipped with a family of opens that are closed under unions and finite intersections and so on. So this is an equivalent characterization of what it means to be a topological space in terms of the neighborhood filters of each point. So I think that's quite cool. I should say at this point that a lot of these ideas about the topological example can be found in the textbook on monoidal topology, although I think you won't find much said in that textbook about the double categorical perspective on this that I'm giving today. Yeah, I think it's very cool that monads in a certain double category give you topological spaces. So okay, I've said what the monads are, but the point of the talk was to talk about morphisms and retromorphisms. So here I'm going to introduce what the monad morphisms are. So a monad morphism from a monad S on A to a monad T on B is going to be a cell of this shape. So on the left, we have S, on the right, we have T. So we have an arrow G from A to B, and then we have a cell gamma that fills in this square, and it should be compatible with the units and multiplications of S and T in the appropriate sense. So what does that mean? Well, it means that we have these qualities. So this is compatibility with the multiplication, this is compatibility with the unit. And again, if you want, you can come back and look at the slides after the talk and have a think about these conditions if they're not obvious. But I think, again, just for the purposes of the talk, it's more interesting to think about what are some examples of monad morphisms. And so in the double category of matrices in V, it turns out that the monad morphisms are exactly the V-enriched functors. So the arrow between the object sets is going to be the object map of the enriched functor, and the cell that fills the square is going to give the Hom maps. So recall that a cell in this double category is a matrix of morphisms. So it goes from, so the AB component of this matrix is a morphism from the AB component of the matrix on the left to the F of A, F of B component of the matrix on the right. So it's a family of maps like so. And then the compatibility conditions that I showed you on the previous slide guarantee that what do I want to say? Guarantee that the composition and the units of these enriched categories are preserved by the enriched functor in the way that you would expect. So the monad morphisms in this double category are the enriched functors. So moving back to the topological example, it turns out that the monad morphisms in this lax Kleisli double category of the filter monad are actually continuous maps. So let's have a think about that. So when I have a cell like so in this double category, so I have the topological spaces X and Y given by their neighborhood filters, and I have some function F from X to Y, and recall that a cell either exists or it doesn't. So it's the existence of the cell is imposing some condition on F, and if you interpret what that condition is, it means that the image in F of the neighborhood filter on X contains the neighborhood filter on F of X. And if you sort of unpack what it means to take the image of a filter, it turns out that it's the same thing as saying that if N is a neighborhood of F of X, then the pre-image of N is a neighborhood of X. And this is also equivalent to saying that the pre-image of every open set is open. And so that's why the monad morphisms in this double category are the same thing as continuous maps. Okay, so we've seen what the morphisms of monads are, but to talk about the retromorphisms, we need to bring in a little more double category theory. But thankfully, Perret also introduced these notions in the previous talk. So what we need is this notion of companion. So as we saw before, so a companion of an arrow F from A to B is a pro arrow from A to B equipped with these cells which satisfy these equations, so I've used this string diagram-esque notation suggestively because these equations look like the straightening of wires. A bit like when you see junctions in string diagrams, the triangle identities look like the straightening of wires. But as Bob said in the previous talk, we should think of the pro arrow F as being essentially the same as the arrow F, but in the pro arrow direction. They're acting in the same way. But maybe it's more illuminating to look at some examples. So if I have so in VMAT, the companion of a function F from A to B is a V matrix, which is given as follows. It's going to be the monoidal unit in all the places where F of A equals B, and it's going to be 0 everywhere else. So if you think of what this looks like as a matrix, it means that every column of the matrix has exactly one monoidal unit, and everywhere else is a 0. Then in the lax Kleisli double category case, the companion of F is going to be the Kleisli map from A to B. So it's a function from A to filters on B that sends each point in A to the filter on B of all subsets of B that contain F of A. So this is a filter. This is a filter on B. So this gives you some sense of what companions might look like. Now, with companions, we can define this new notion called a retrocell. So this was also introduced by Bob in a talk a few years ago. So the idea of retro cells is it kind of allows you to talk about cells where the cell goes in the opposite direction to the arrows. So notice here in the retro cell, the arrows are going backwards, but the cell is going forwards. So a retro cell of this shape is really just a cell in your double category of this shape, where you've got the companion of F on the top and the companion of G on the bottom. And you've got N and M like so. So you can almost think of it as if we sort of, we're thinking of this companion of F as really being coming back in the backwards direction, and this companion of G is being rotated and going back in the backwards direction as well. So this is what a retro cell is. And the point is, given any double category D with companions, you can form a new double category whose cells are the retro cells in D. So these retro cells compose in both the horizontal and the vertical direction and satisfy the interchange law and so on. So you can form a double category of retro cells. But I'm not really going to talk about that much more today. So we have this notion of retrocell, and with this notion of retrocell, we can define what a monad retromorphism is. So a monad retromorphism from the monad S to the monad T is a retrocell of this shape. So I guess there's you have to choose some direction for the retromorphism, and I've chosen for it to go in the same direction as the arrows rather than the cell, because this convention aligns with the usual convention that Bryce and I use for cofunctors. But you could, of course, choose to make it go in the same direction as the cell instead. That would be a different convention. But so the idea is is that the cell for this monad retromorphism is going in the opposite direction to the arrows. And this should be compatible with the units of multiplication of S and T. And this compatibility condition looks very similar to the compatibility condition I gave before, except that these are now diagrams of retrocells. You'll notice that the G is going in the reverse direction. And I guess I should say the point is that whenever you have one of these special cells, so by special cell, I mean cell with identity arrows on the top and bottom, then it is also a retrocell. So special cells are both cells and retrocells. And so we can interpret these as diagrams in this retrocell double category. Okay, so that's what a monad retromorphism is. But again, I think it's more illuminating to look at some examples. So for the first example, the monad retromorphisms in the double category of matrices in V are the V retrofunctors, or also known as V cofunctors. So these, so the notion of enriched cofunctor was introduced by Bryce and I earlier in this year. So Bryce gave a talk at ACT, and then we've recently put out a preprint about the enriched cofunctors. But cofunctors in the set enriched case have been talked about for a number of years now. But so how do these relate to retromorphisms? Well, so a retromorphism, recall, consists of an arrow. So if I have an enriched category C and an enriched category D, then the arrow phi is going to go from C to D. And then it also consists of a retrocell. So notice that the retrocell is shaped like so. And if we want to interpret what it means, or we need to interpret what is this matrix product on the left and what is this matrix product on the right. And so if we sort of look at it, it's going to be a matrix. So because we're in the double category of matrices, it's a matrix indexed by the objects of C and the objects of D, where the C D prime component is a morphism from this product, or well, sorry, this element of the matrix product here to this component of the matrix product here, which if you sort of simplify things a bit, it amounts to having a morphism from the Hom object from phi of C to D prime into this sum over all C prime in the D prime fiber of phi of the Hom object from C to C prime. So this morphism here is, you can think of as a lifting morphism. It tells you how to lift morphisms out of phi of C to C itself. So, and this is where, like, it's the action on the morphisms is in the opposite direction to the action on the objects. So this is how we can see that these V-enriched retrofunctors are really just monad retromorphisms in this double category of matrices in V. Okay, so let's look at our other running example. So the Lax-Kleisley double category of the filter monad. So it turns out that the monad retromorphisms here are the open maps of topological spaces. So what does it mean to be a monad retromorphism here? Well, again, we have a function phi from x to y, and then we have some retrocell. But recall that in this double category, it's a flat double category. So either such a retrocell exists or it doesn't. And the existence of this retrocell, when you unpack what these, because these are Kleisley composites, when you sort of simplify these composites using the monad axioms, you get this condition here. So the neighborhood filter of phi of x should contain the image in phi of the neighborhood filter on x. And when you unpack what the image of a filter is, you get this condition here. So if n is a neighborhood of x, then phi of n is a neighborhood of phi of x. And this is also equivalent to saying that the image of every open set of x is open in y. So the monad retromorphisms are the open maps. Okay, so what's next? So the final thing, because we're moving towards building a double category of morphisms and retromorphisms, is we need to talk about the cells. So a monad transformation, like so here we've got so the objects are the monads, the morphisms are like so, that the arrows, the retromorphisms are like so, they're the pro arrows, and now we're defining what the cells are that fill in these squares. So a monad transformation like so is going to be a cell of this particular shape. So it involves G on the left, E on the top, F on the bottom, and H on the right. It also involves S, which is the monad up in the top right corner here. And it looks kind of asymmetrical, but it turns out that there's an equivalent formulation of what a monad transformation is, which also has a copy of R down in the bottom left-hand corner, which sort of brings the symmetry back to the whole thing. But the R in the bottom left-hand corner turns out to be kind of redundant, which is why we present it in this way. So it's a cell of this shape that satisfies this condition here, which again, maybe looks like quite complicated, looks like a lot, but there are ways of sort of massaging this diagram to make it look a little bit more symmetrical or make a little bit more sense. But the point is that this is exactly the right definition of cell to give, such that when we look at the double category of matrices in V, the monad transformations corresponds to natural transformations. So most of you are probably only familiar with natural transformations between V-enriched functors, but it turns out that you can also define natural transformations between V-enriched retrofunctors and actually natural transformations that fill in squares like this, where the top and bottom morphisms are V-enriched functors and the left and right morphisms are V-enriched retrofunctors. And all of this is in the preprint that Bryce and I put out about the V-enriched retrofunctors or cofunctors. So that's what a monad transformation is. And with all of these definitions, we can now say what the double category of monads and monad morphisms and monad retromorphisms is. So if D is a double category with chosen companions, then we can form this new double category, which I'm denoting MND ret of D, whose objects are the monads, whose arrows are the monad morphisms, whose pro-arrows are the monad retromorphisms, and whose cells are the monad transformations. And when we do this to VMAT, we get what I'm denoting by VCat ret. So this is the double category of V-enriched categories, V-enriched functors, V-enriched retrofunctors, and V-enriched natural transformations. And if we do this to this Lax-Kleisli double category of the filter monad, we get the double category of topological spaces, continuous maps, and open maps. So this is where I'd like to end my talk. In summary, we saw that double categories with companions are a good setting for understanding general notions of lifting. So in particular, this notion of retrocell, which sort of has this flavor of some things going in one direction and other things going in the other direction, allowed us to define this notion of monad retromorphism, which turned out to, in certain double categories of interest, correspond to known and interesting kinds of morphisms. So the cofunctors and the open maps. What I didn't get around to talking about today is that there's another notion of cell that to form another double category whose arrows are monad morphisms and whose pro-arrows are monad retromorphisms. And these are so-called compatible squares. And you should think of a compatible square as kind of like a commutativity condition for a square where you have a mixture of morphisms and retromorphisms. And with this notion of compatible square, you can define what a lens is. So at the start, I mentioned in our examples, if you have a compatible pair of a functor and a retrofunctor, what you have is called a delta lens. If you have open map and a continuous map, then you get an open map. And so in the general setting, you can define what a lens is, and it corresponds to these concepts. What I also didn't talk about is you can play the same game to get internal category theory. If instead of starting with the double category of matrices in V, you start with the double category of spans in a category C with pullbacks. Or if you want to do categories internal to a monoidal category, you could start with the double category of bicomodules in a monoidal category with nice equalizers. Now, some things for future work are really about understanding this construction of the double category of monad retromorphisms. So we know that there's a relationship between monad retromorphisms and bimodules. So just as every monad morphism can be seen as a bimodule, I think you need companions to do that. Every monad retromorphism can also be seen as a bimodule in a certain way. And so then you can view these, all sides of these squares of monad morphisms and retromorphisms as really just squares of bimodules. And so I think there's something that to be thought about there in terms of the relationship between these ideas and bimodules. Another thing to think about, so one of Bryce's ideas that he likes to talk about is this idea that a cofunctor can equivalently be viewed as a span of functors of certain type. So every cofunctor is a span whose left leg is a bijective on objects functor and whose right leg is a discrete op vibration. And this turns out to be the same thing as saying that this double category of categories, functors, and cofunctors has effective tabulators, which is something that Bob talked about in the previous talk. So an interesting question would be to ask, so what conditions do we need to impose on the double category D so that the double category of retromorphisms in D has these effective tabulators, or has this ability to represent retromorphisms as spans of morphisms? so another direction for future work, which is relating to these lenses, is when is it possible to do this thing called a proxy pullback of lenses? So it's kind of like a pullback that's I don't know, maybe I don't need to say much about that here. And obviously, I think it would be cool to find even more examples of double categories, which when you apply this construction yield familiar notions. So in this case, we got the familiar notion of topological space, open map, continuous map. We got the familiar notion of categories, functors, cofunctors. What other kinds of examples, interesting examples might be around? So the final slide, which you can find if you look at the talk at the slides, will be some areas for potential further reading, but this is where I'm going to end the talk. So thank you for your attention.
Okay, thanks, Matt. With a silent round of applause. Are there any questions for Matt? If you have a question, just raise your hand and you should be able to unmute. Yes, Bob.
You're on mute.
Okay, good. Your double category with your example with topological spaces. Why not just take open maps in the direction? You know, the usual definition of open map, the direct image of an open set is an open set, and for the retro ones, take the continuous ones where now you're mapping open sets backwards. So,
right.
Yeah.
So that is a good question. So I guess, so in one sense, it's the way it comes out of the theory is that the continuous ones are the morphisms and the open ones are the retromorphisms. But I think the point was, when I was back in the introduction, I was trying to motivate this through this other perspective in terms of filter convergence. So when you look at it in terms of filter convergence, I think it sort of is a bit clearer that, or maybe this is more of an analogy with things like categories and preorders and things. So the continuous maps preserve the filter convergence, whilst the open maps lift the filter convergence. And this lifting property is very similar. For instance, if you go to, so on the enriched category setting, if you enrich in the monoidal category 2, so it has two objects, say true and false, and a morphism between them, then the enriched categories there are preorders, the enriched functors there are monotone maps, and the enriched cofunctors there are what I'm calling retromonotone maps, and they satisfy a very similar kind of lifting property. And the point is that preorders can equivalently be viewed as topological spaces, as so-called Alexandrov discrete topological spaces. And under that equivalence, the monotone maps really are continuous maps, and the retromonotone maps are the open maps, and the preorder itself is kind of like the reverse of this filter convergence relation. So this filter convergence relation is like a generalization of this specialization preorder. So that maybe gives some other reasons why, even though the continuous maps sort of lift open sets and the open maps preserve open sets, the continuous maps really should be the morphisms, and the open maps really should be the retromorphisms. Does that answer your question?
Yes, yes. Okay, thank you.
Cool, thank you.
We have time for some more questions, if there are any.
Hi, can I ask my question?
Yes.
Hi, so first of all, great talk. Second of all, what is the relationship between like functors, retrofunctors, and profunctors, or replace functor with morphism, as you like? So can you involve profunctors in this picture, or are these orthogonal generalizations, let's say, of functor?
Yes, great question. So I guess maybe, so I did actually mention this on the last slide, but I used the term bimodule rather than
Right.
Yeah. So in this picture of enriched categories that I was giving before, so we're looking, we've got monads in VMAT of V categories, and then the monad morphisms in VMAT of V functors. So you can also define what a bimodule is for if you've got a pair of monads, a bimodule is a certain cell satisfying certain conditions. And the bimodules in VMAT are the V profunctors. And then with these companions, you can turn a V functor into, you can turn a monad morphism into a bimodule in a certain way. And similarly, you can turn a monad retromorphism into a bimodule in a certain way. And so in the setting of V matrices, this amounts to saying you can turn a V functor into a V profunctor, you can turn a V cofunctor into a V profunctor. So does that answer your question?
Yeah. Can I ask a follow-up just
Sure.
to make sure I understand? So ideally, there's something like a triple category in which you have the three of them, and then you have some sort of companionship between functors and profunctors, retrofunctors and profunctors. Something like this.
I could imagine such a thing, but I would, thinking about triple categories, it's like a level up in my sort of theory thinking. I think, but yeah, I could imagine you could do such a thing.
That's very cool. Thank you.
Thank you.
We probably have time for one more question, if there is one. So maybe just a short question from me, which is that you sort of mentioned that this filter monad is kind of similar to the power set monad on set, and you're constructing this sort of ad hoc double category, this Lax-Kleisley thing from the filter monad. Do you expect that you could also do something like this for the power set monad?
Yes. If you do this for the power set monad, I think you get the same thing as the double category of matrices in, like, if you take two, that monoidal category 2 that I was talking about before, and you look at 2MAT, I think that should be the same thing as if you do this sort of ad hoc KL-Lax thing to the power set monad.
Okay, that's interesting.
The Kleisley morphism of the power set monad is a relation, which is also the same thing as a matrix of true and false values, right?
Right.
So I think yes is the answer.
Okay, thank you. Okay, and I guess we should wrap up questions there. So let's thank Matt again for the talk.